Hello. I recently did this project that you can see over here where I used the L system SOP in TouchDesigner to create these procedurally generated plants in real time. And I wanted to discuss some tips and tricks that I learned along the way and also share a component that I created called L System Plus that incorporates a lot of the best practices and additional features that I used for this project. The first thing I wanted to do was go over some resources. I found it a little bit tricky to find good learning resources when I was starting out, so these were the ones that were most helpful for me. Always a good place to start is the TouchDesigner docs, and this page has a lot of info. It took me quite a few reads to understand all of this, but I would just encourage you to keep coming back as you learn more. One particularly helpful section is this that talks about all the turtle operators. I would probably copy paste this into whatever editor you're using to edit rules, because that's very important. The next one is The Algorithmic Beauty of Plants, this book by Lindenmayer. And L system, L stands for Lindenmayer. He's the mathematician who created this system. There's a lot of really detailed, great information in here, and there's a lot of rule sets that you can port to TouchDesigner fairly easily and get some cool structures, this kind of stuff. The next one I wanted to mention is this workshop by TDSW, Akiko Yamashita. This was super helpful for me, and a lot of the techniques that I'm going to show later were learned from this workshop, so I wanted to give a big shout out there. This next one is something that I found from that workshop, and this one's awesome. This is probably the main one I would recommend. It is targeted towards Houdini users, but resources about L systems and Houdini can be pretty much directly applied to the L system SOP in TouchDesigner. They're very similar. But this goes in really good detail through all the different operators and all the different concepts, and has a bunch of rule sets that you can really easily adapt to TouchDesigner. So yeah, this is an amazing resource for sure. The last one is this tutorial that I found, also targeted towards Houdini users, but I just found it was a really helpful visual breakdown of how to think about L systems, and he walks through the creation of one. So if you're a more visual learner, I guess this would be a good one. The first thing that I did when I was starting with the L system SOP is to look at the operator snippets, which is always a handy way to look at a new operator. And that's where I got these nodes to start with. The first big question that I had was, how do I separate the trunk or the branches from the leaves and color those independently? Because I think you'd probably want to do that for pretty much every case. I'm going to disable this animation, just set this to be 5 works, and just show you what I mean. If I were to try to create a rendering setup, I'm just going to add a geo, a camera, a light, and a render top. And then if I add a material to this geo, you can't really independently color the different parts. It's all going to be the same material. So the first way to solve that problem is one that I found on the forum, which is that you can add a delete SOP. If we plug this in here, you'll see you can select a group, and TouchDesigner, this SOP automatically creates groups based on the leaves. You can actually set the prefix for those groups in here. So if I wanted to isolate the branch, I could select LsysJ and LsysK, and that will delete both of those groups. And I could then plug this in and have just the branches rendering. If I then wanted to separate out just the leaves, I could say LsysJ, and instead of delete selected, delete non-selected. That's going to use just that. So if I now create another geo for this, and let's create a new material for these, we'll just set that to be green. Now you can see we have the desired effect here. And of course, you could do the same thing with the other leaves. What I found when I was doing this, if you pull out the probe, which is always a handy way to optimize networks, you hit Control P and it shows you this display and says which operators are causing significant computer usage. Nothing is happening right now because this isn't animating, so I will just we can just animate this angle or something. Seconds. That should now mean that everything is cooking. What you'll notice is that these delete SOPs that are removing some of the SOP geometry has basically the same amount of cooking required as the original L system, which is just a little bit inefficient. It's basically just adding an extra operator. So eventually I came up with this alternative method to separate out the different geometry of the L system that I wanted to share. So I'm going to delete these delete SOPs for now. And the basic idea is, what if instead of deleting and isolating the geometry after it's already made, what if we could customize this L system to just render that specific geometry? So we have three components here, which is the base and then leaf J and leaf K. So I'm going to duplicate this L system a couple times. And the idea I had was, what if we could customize this rule dat so that it will only render the geometry you want? And the way we can do that is with the substitute dat. So if I pull this in and plug this in here, if I wanted to get rid of all the J leaves, I could just say before is J and after is nothing. And that's going to get rid of the J leaves. So if I then plug this in, it's a little bit hard to tell right now. I'm going to get rid of this. But there are no longer any circles in here. The substitute dat can take in a table as the source too, and that is how you can configure these all at once. So I'm going to copy paste these substitute dats that I made earlier to save some time and show how these are working. I have tables here that are set up to substitute it so that only the base will render, and then only leaf J will render and only leaf K will render. So to isolate the base, I'm just replacing all three of the leaves with nothing. To isolate the leaves, I'm removing the other leaves, but I'm also replacing uppercase F and H with lowercase f and h. Uppercase F and H are the two operators that move forward and create geometry. H will do half the length, F is full length. And you'll notice these options right below that says move forward but don't create the geometry. So it'll create the same structure, but it won't actually create that base geometry, which is what we want. So if I now take this onto the first L system, we'll get rid of these dats that are no longer used. And yeah, you'll see that this first one is just the base, second one is just the circles, third one is just the triangles. These substitute dats are part of the component that I'll share later, so you don't need to worry about like copying those out. So now if we then plug these into the geos, I'm going to create another geo and material for the third one. We can get, let's see, doesn't want to plug in. There it is. And now after adding these attribute creates, we're getting a similar sort of effect as before, where we have each of them colored differently. So now if we pull up the probe, you'll see that we just have three intensive operators to create the three geometries, and there's no extra delete SOP operations. So it's just more efficient than the delete SOP method. So another quick tip I wanted to go over is about limiting the generations of the L system SOP. As you experiment with more rule sets, you'll notice that some of them are way heavier than others. So if I bring in this other one, the FPS takes a little hit, and if I go up to 5 generations, it's basically frozen. And you can get into some dangerous scenarios where your computer might crash. So I wanted to have a way to avoid crashes. To set this up, I'm just going to create a new component so we can add some parameters. Let's put all this inside. And I'm going to add a couple parameters here. One is going to be generations, and let's do rule dat for the other one. I'm going to take this out, and these dats will be selected at the component level. Rule dats, parent.par.rule dat. Cool. And then let's set up the generations. So the idea here is basically what's a simple way to limit the number of generations tied to each rule set. And the way that I started using was adding a digit to the end of these dats and saying that for this rule, I want this digit to be the maximum number of generations that are allowed. And that can be set up with a simple expression where inside here I can say, instead of just parent.par.generations, let's do the math.min of parent.par.generations and op of parent.par.ruledat.digits. Let's see what my issue is there, math.min. Oh, I guess it's just min. Right. So let's set this to like 7. And because of this digits expression, this is going to be limited to 5. Digits just gets the last digit in the name of an operator. And the nice thing about this is, like, you know, maybe I'm playing around and I have generations up to 10 for a particular rule set. And if I were to drag this on and it actually went to 10, my computer would crash right there. But because this is limited to 3, we don't get a crash. And I think it kind of makes sense to tie it directly with dat because the complexity of the system is kind of like inherent to the rules themselves. The next big tip I wanted to go over is something I learned from the TDSW workshop. And basically you can use instancing to instance and render these leaves instead of creating the geometry within these SOPs. And that makes the network more efficient, and it also allows for a lot of customization of how those leaves look. So it's a really cool technique. It starts off with these 3 SOP operators that I got from that tutorial. And this is basically creating a singular point with all the point attributes we need. It's got a normal, up vector, and UV as well. And that works by starting with the line SOP. It's just creating a vertical line. We use the point SOP to add a couple of those attributes, adding a normal and an up vector. And then finally we scale it down on the y-axis. So it's just a single point. And that's about the simplest instancing setup you can get, which is nice because it's really easy for these L system SOPs to render those and create that geometry. So I'm going to replace the circle and triangle and plug this in instead. A couple things to note is that in order for this technique to work, you need to turn this to skeleton and also get rid of this attribute create. That will just mess with the attributes that we've attached to all those points. So once those are changed, we've got these nulls that I've added, and we can use these as the instance operators for these 2 GS. So let's start with leaf J and set this here. And I'll pull in the circle we were using earlier as the input. When we look at the options for translate, we get P0, P1, P2, which is the point position. These are huge. So let's add a transform SOP and just set that to 0.01 or something. Right now they're all facing the same direction, so let's add in the normals as rotate 2. And finally the rotate up for our up vectors. And we'll increase this. Yeah, looks like this might need to be rotated, plenty to play around with here. But basically, we get pretty similar results as we did using the L system to generate that geometry, but a lot of that work has been moved to the GPU, so it's quite a bit more efficient. I've gone ahead and done the same with this other leaf and also just added a different SOP to make it slightly more interesting. The next really cool thing that you can do with instancing is to start to customize these instances, because there's all these properties of the instances that you can customize. So I think a good place to start would be the scale. We can use a noise chop to create somewhat random scale values across the instances. So because we want one sample in this noise chop for every instance point, we can use a little expression to set that up. This is going to be for leaf J. So if I go to the channel page and set this end to be op of null leaf J dot mem points, that's a member that this has, -1 actually, because it starts at 0, not 1. So now we have this noise where we've got a sample for each instance. I'm going to customize the values a bit. So we'll start with a limit chop and normalize them to be -1 to 1. And then we can use a math chop. We can make that, let's say, 0.2 to 2. I don't know, we can figure that out. The way to attach this chop to the SOP as an attribute is using the chop to SOP. So I'm going to put this between the null. The way this works is it uses the input as the starting geometry, and then you can use a chop to add attributes to that geometry. So I've selected the null here. I'm going to change this to be scale, because that's the name of our channel. And I'm going to map scale to an attribute called scale. You can kind of call this whatever you want, and if you middle click, you'll notice a new scale attribute has been created. So I'm going to plug this in to the null, and it's now being referenced by this geo, and you should see that new attribute pop up here. Yeah, so this can be customized however you want. The highest could be higher, the lowest could be lower. You can change the period of the noise. Maybe it could be cool to add some animation so that they're kind of moving over time. So that's the basic idea, is using a chop to create values for an attribute and then referencing that in the geometry instancing. So I switched over the scale to control the shape of those spheres, and I'm going to stop animating this, but we're going to try something else with these leaves now, which is referencing the actual geometry to determine your chop values. So before this chop 2 of leaf J, let's do a SOP to chop. And this gives us information about the SOP. So we have this TY parameter. That's what I'm going to use to change the scale of the leaves as the plant gets higher. Something you'll see a lot is that the leaves at the top are smaller than the leaves at the bottom. And maybe we can change the angle a bit so that'll be more obvious. So once we have the information here, I'm going to select just the Y channel. And I'm going to do a similar process of normalizing. So let's use the limit, normalize, and here we can use math to remap this channel. We can say -1 to 1, let's go, 0.1 to 2 or something. Because this null is being used in both these chop 2s, I'm going to create a merge chop before that, so we can add all these together. Actually, I'm going to use a different null for the different leaves. So let's get rid of this one and add this one instead. And I'm also going to rename this one to be scale, because that's what we want it to control. Now if we do the same sort of thing here, scale, scale, reference that in this geo. Yeah, basically what we've done is remapped the TY channels to determine the scale of these. So I think I actually want to invert these. We'll do 2 to 0.1, and you'll see that they get smaller at the top. It doesn't look amazing right now, but I think it gets the point across. Just using sort of gradients of values that can be determined based on TY. You could do any of these parameters. You could add them up so that each point has a unique index value. There's a lot you can do there. The last example I want to show you is how you might want to add color to the instances and change the color across space. So how we can do that is, first let's create a ramp top. And this is going to be the gradient that we use. It could be anything. Blue and gold or something. Why not? We're going to add a top to chop here to get those chop values. And then we can use a lookup chop to map the position of each instance to get a specific sample of this color along the gradient. So if I plug this into the bottom, and we're going to want this top one to be in the range 0 to 1, because that's how the lookup works. So I'm going to create a new math, and let's say -1 goes to just 0 to 1 now. And let's use TY for now. So we want the one that's limited, so it's just -1 to 1. And we'll add this here. Now we've got 3 channels that should be corresponding to, I'm going to get rid of A, should be corresponding to the vertical position. So I'm going to add this merge and use that as the null. So now that these RGB channels have been added into this null, we can add them to the chop as usual. So I'm going to say RGB, and the equivalent attributes for color are CD0, CD1, and CD2. It's nice to be able to see what you're working with in this dropdown. Now those attributes should be available in the geo. I've changed this to white, so we'll be able to see it a little better. And if you go to the second instance page, there's this color section. So we can say CD0, CD1, and CD2. And that will use the gradient defined here across the y-axis. So, this could be changed however you want it. Another thing we could do here is use a different lookup. So maybe instead of the y-axis, we want this random noise. It looks like this noise would need to be scaled up a bit because most of it is not in the 0 to 1 scale. Yeah, so anyways, that just shows how you can use the lookup chop to add color to instancing. Finally, I wanted to talk a bit about this component that I created, and I'm going to share a download link in the description. But basically just encapsulates a lot of these techniques that I've discussed. So if you pull up the parameters, there's a lot of custom parameters in here. This first page just deals with the basic setup, choosing the base material, resolution of the render, and then also exposes a lot of the parameters of the L system SOP. I also added this grow parameter as kind of like a master slider that I've mapped to a lot of other things. So you'll see me.par.grow is referenced in a lot of these expressions. Just kind of a handy way to control an animation. And then if we look at these leaf pages, it has a lot of the parameters that set up the instancing functionality. You choose your material, your SOP. This point leaf toggle determines whether the leaves will point in the direction defined by the normal. It can be useful to turn that off in cases like fruit where you want them to be just hanging down. And then you can control the scale and the color using these parameters. So the scale type, you can select constant, just keeps them the same, vertical, which controls them vertically, and the noise option. And then this scale range, you can set like, I want the biggest ones to be that big, smallest ones to be very small. Then you have the color type, which is very similar concept as the scale, but just for color. And you can add a ramp to determine which colors you want to use. If you're using noise, you can change the noise period and the translation. So you can get some animations that incorporate both the scale and the color, which is kind of fun. And the same thing goes for leaf K and leaf M. You've got all the same possibilities there. So if we take a look inside, it incorporates all the techniques that I've talked about, uses the substitute DATs to separate out the different geometries. And then there's these leaf components that I created that add all the attributes for scale and color. Yeah, I guess the last thing would be this little execute setup down here, which will turn off these geos based on whether the character is present in the rule dat. Found that even if it wasn't rendering, it would still be cooking a little bit if the character was present. So I just thought this might optimize things a little bit. And yeah, that's about it. Feel free to use it as is, or also just use it as a starting point and go in here and pick it apart and change it. I'm sure things like this rendering setup could be improved with more lights and stuff like that. Thank you for watching. I hope this was helpful. And like I said, I'm going to share the download links to this demo file as well as this talks file that you can drop into any of your projects. So yeah, let me know if you have any questions.